Hi, welcome back to another episode of pollys Introduction to Computer Networks. Well, you know what, guys? There's nothing more to say except that at 1 p.m. today, exam 1 results will be out. And hi, Sylvain. Okay. Yeah, good morning to you all. And glad that you're here early because the first topic today is quiz 20. Okay, I hope that you guys are all waiting for it to come. You know what? It's coming right now. So quiz 20 here is to exercise RDT 3.0. Hi to you all. Sorry that we don't have time to say hi one by one today. Yeah, let's go ahead and check out the RDT 3.0 and see if you can exercise that finite state machine set with 2 scenarios, S1 and S2. By the way, these 2 scenarios are not related. Okay, for each scenario, you need to tell me the transitions that will be triggered in sequence. So on the left is the sender side of RDT, and on the right, the receiver side. So S1, if we send 1 packet, but the packet is lost, so never reach the receiver, but there will not be any more losses, bit errors afterwards, and there's not more packet from the application layer. Okay, what will be the transitions triggered in sequence? For scenario 2, this is the tricky one. Okay, sender here sends one packet, and then the receiver returned ACK1, an ACK packet with sequence number 1. Okay, and this packet is received by the sender. But the sender, after doing the checksum, finds a bit error. All right. Okay. Luckily, there is no more losses or bit errors afterwards. Okay. What will be the sequence of transitions triggered? Okay. So that's quiz 20. Let's go on to the Discord channel WA quiz 20, and this time we'll take the fast, complete, correct solution for the bonus. And you guys have 3 minutes. Let's go ahead and start. Tao, Miguel, hi, but hey, go on to the W8 quiz 20. Quiz 20 has already started and we are taking the fast solutions. Okay, we still don't have correct solutions yet. Okay, it's very interesting. So how about 2 more minutes? time's up. Yeah. Okay, so we know, right? So for scenario 1, so maybe I can move back to, for scenario 1. For scenario 1, okay, it's obvious. If we send one packet, but the packet is lost, so send one packet means we trigger T1, because the starting state is here and here. Okay, as we walk through the finite state machines. This packet is lost. Okay, so it's sent out, but get lost. So what's going to happen there? Well, receiver won't be triggered at all, right? Because packet never get to the receiver. So what's going to be triggered next? Yeah, so the timeout would happen next. So T1, T3, and then we retransmit, right? So send it again, and it will pass T11 and then T4. So you guys get the first quiz right, first scenario right. But the second one, okay, S2 here, independent from S1. As you guys also say, the first transition will still be T1, okay? But this time, the receiver gets the packet, and it sends back a AG1. So which transition sends AG1? So you guys all say T12 or T11? So let's see, T11 sends what? AG0. Which transition sends AG1? Yeah, so it should be T14. T14 sends AG1. That means this data packet going out might be corrupted, or it's carrying sequence number 1 that is not expected. Yeah. But hey, so in this case, obviously corrupted. It's carrying sequence number 0, obviously, right? So that data packet is corrupted, therefore AG1 is triggered. Now when the sender here receiving AG1, what does it do? Well, if it's exactly AG1, then it triggers T2. But it's got a bit error there in the return AG1. So hey, in that case, we also trigger T2. So it should be T1, T14, T2. And then what happened? And then timer will fire it again. T3, T11, T4. Okay. Yeah, it's really tricky, isn't it? Let's see. Yeah, so I have to say, guys, you guys actually managed to update the solutions after Polly mentioned this. So hey guys, as long as you try to correct back, you get the credit for the quiz, but no one gets the bonus this time. Okay, yeah. So guys, this is just for you to know that, yeah, you want to be fast, but you want to also think the question through. Okay, good. So we did say that we are sending a data packet to the receiver, and receiver sends back AG1. Okay, so T14 is the next one triggered, obviously, in the scenario. And then T2, and then we wait until there's a timeout, T3, T11, T14. Yeah, so I think team 4 and 5 got these right eventually. 6. T6. Okay, so yeah, Yongxiang here is probably assuming that S2 continues from S1. No, Yongxiang, they are independent. So you start again from the starting state. But it's okay, I get your point. Maria, good. Zach, good. Okay, Sophia, it's a little bit tricky, isn't it? Think about it again. Nick, Jeremy, Tao. Very good. All right. And let's go on to the next topic. Okay, so we just finished talking about the very basic form of RDT. So RDT 3.0 this time, we know it will work with the underlying channel with bit errors as well as packet loss. Okay, an unreliable channel do have these two kinds of errors. Now, RDT 3.0 works, but there's a serious issue. In this next video, Polly is going to introduce you to the issue. Okay, it's a performance issue. And the first part of the video is to define a new metric called utilization. Okay, so between the sender and the receiver of a connection there, you have a channel. Okay, and how much you're using this channel is called the channel utilization. So this video is a bit long because there will be an example showing you how low the channel utilization is with RDT 3.0. RDT 3.0. We spent quite a lot of time talking about it, and finally it seems to be working for the bit error case and the packet loss case. And you know what? It works indeed, okay, but it does not work that well. Okay, let me use this example here to explain. So let's suppose we have a pair of sender and receiver. In between them, there is this link, 1 gigabits per second. Okay. And the propagation delay one way is 15 milliseconds. And between the sender and receiver, the packet size is 8,000 bits. And that is the equivalent of 1 kilobyte. So this is very typical of a TCP connection's packet size. And you see also earlier doing the trace routes, 15 milliseconds is very typical between two routers on a local area network. And 1 gigabits per second link, this is very commonly seen. Some of the Ethernet connections are actually 10 gigabits per second already. Now, let's try to calculate. First, the transmission time. Well, you learned already in chapter 2, right? It's the packet size divided by the transmission rate. So packet size, transmission rate, 1 gigabits per second. And we get 8 microseconds as the transmission time. Now, the performance we'll be looking at here is this, the utilization of the link between the sender and receiver. Okay. If this is high, that means, ooh, sender is actively sending all the time. So usually the throughput is going to be better. Okay. But if the utilization is low, the throughput is not going to get any better. All right. Now, in order to calculate the utilization, let's recall how RDT 3.0 works. We send from the sender one data packet, and the sender there stop and wait for data to travel to the receiver. Receiver sends back an ACK, and ACK travel the network again back to the sender. And that's when the sender can decide whether to send another data. So sender there again stop and wait until data travel to the network, ACK travel to the network, and then send another one. So you see that the sender there is working in cycles. Stop and wait, stop and wait, stop and wait. And each cycle, it's using this much amount of time to transmit actual bits, and this amount of time, so plus the round trip wait entirely for the entire cycle. So this is 0.008 millisecond, and this part, sending the packet and then wait, one wait and another wait. And here I'm ignoring the ACK packet transmission time because ACK packet is usually just very small. Okay, so that's one round trip time plus packet transmission time, 30.008 millisecond. So overall utilization on this link is very, very low, 0.00027, too many zeros. And if I illustrate the scenario I just described there, sender, receiver, and this is timeline, okay? At time 0, first packet bit is transmitted. So right here, first bit goes onto the link. And it takes this amount of time, that is the time to transmit all bits on the packet. So last packet bit transmitted is right at this time, okay? That is the packet transmission time, L divided by R. And these bits is going to travel halfway to the receiver and another halfway back to the sender. So first packet bit arrives right here. This is what? The propagation delay. Okay? And this is also propagation delay. So 2 propagation delay plus L divided by R. This is one cycle. Within a cycle, only this amount of time sender is being active. Okay, only this amount of data is being transmitted. While the entire duration, right, the sender can just keep pushing bits out, okay, onto the network interface. So you see again, the network utilization, L divided by R over the entire term, RTT plus L divided by R. Very low utilization. And that low utilization can be translated here. The throughput on the 1 gigabit link is only 270 kilobits per second. This is not even enough to send any video that would be sensible. So you see here, RDT 3.0, the design itself, although it works, but it limits the use of the physical resources. Okay, we're only sending one packet and then stop and wait until we can send another one. Now that I show this plot, then you know, yeah, obviously to increase the utilization is to send multiple packets per round. Indeed. So let's look at the plot in a bit more detail, just like we did in the previous slide. So sender, receiver, and timeline again. So this is the time we send the first packet, the end of the first packet. This is the time, first bit arriving at the receiver, last bit arriving at the receiver. At this point, the receiver can send back acknowledgement. So this is the time the acknowledgement arrives at the sender. This is the sender can begin sending the next round of packets. So how long is a round this time? Well, this is one-way delay, right? This is also one-way delay. So round-trip delay plus L divided by R. So the same. In each cycle, we now send multiple copies of packets. So now we're sending 3, so 3L divided by R, right? So utilization is now 3 times higher than the stop and wait scenario. All right, so then you can imagine those mechanisms that allow us to pipeline multiple packets in one round are called the pipelined RDT. Okay, the principle of such kind of RDT is very similar to RDT 3.0, but there's a little bit more complexity to handle sending multiple and tracking multiple packets being sent in one round. Okay, so in the next video, Polly introduced the pipeline RDTs. They're in generally 2 flavors. One is called go back in, the other is called selective repeat. And this takes us to this new class of RDTs called the pipelined protocols. Okay. What it said is, let me repeat myself, the sender allows multiple packets being sent per round, okay, or multiple packets in flight. By in flight, I mean that these are just data packets going out. They are not yet acknowledged. So it's illustrated better here. So this one on the left is stop and wait. This one on the right is the pipelined RDT. So we see multiple data packets go, not yet acknowledged, and their acknowledgements will come back in a sequence, okay, in a round to the sender. Okay, so a range of sequence number needs to be increased. So previously in RDT 3.0, we used just 1 bit, right, 0, 1. But now we need to allow multiple packets going out simultaneously. And we need to make sure that we acknowledge each of these packets. So we need to tell each of these packets in flight apart. Well, the sequence number definitely needs to be expanded. And we'll need buffering at the sender and the receiver side as well. Because, hey, what if multiple of these packets in flight are dropped? They need to be retransmitted again. So buffer definitely at the sender side is required to store those packets that are not yet acknowledged. Receiver here will also need buffer space because when this packet is lost and there's other packet coming in subsequently, should we keep them or should we drop them and have the sender retransmit again? And what about these other packets that has already arrived? Okay, so there's some buffer space also, okay, needed in order to address different needs of different designs. So buffering required, a longer range of sequence numbers required. Okay, now in the next few slides, what we're going to introduce are just 2 different flavors of these pipeline protocols. So they are the big categories.
First is the go back N. The second is selective repeat. Now one can of course further tune the go back N so that it works slightly differently. Hopefully the second version works slightly better than the fundamental version. Similarly for the selective repeat protocols. Okay, so here's the overview slide that contrasts the two big categories of pipeline protocols. On the left, the go back N. On the right, selective repeat. Right? They are the same this way. Okay. Both of them allow having multiple packets in flight in a round. Okay. Well, that's the basic ideas of pipeline protocols. They must be the same this way. And then everything else will be different. First of all, okay, what the sequence number in the ACK packet means very different. One is to indicate I'm acknowledging an individual packet. So when the receiver in selective repeat sends an acknowledgement, that sequence number in the acknowledgement is to acknowledge exactly the data packet carrying that sequence number. But for go back N, the receiver sends back acknowledgements, but the acknowledgement carries a sequence number such that all the data packets before that sequence numbers are acknowledged. So this is a bit odd. Okay, so that one sequence number seems to be acknowledged all the packets before that. But the fact is that what the receiver is doing is this. The receiver will not add packets if it arrives and the receiver finds that there's a gap in between. So packet 1, 2, 3 missing, 4. Okay. When 4 arrives, the receiver does not send back acknowledgement 4. Instead, it sends acknowledgement 2 because there's a gap in the middle. So what the receiver of go back N here is saying is, I'm actually telling you to which point I do have consecutive receive data packets. So the next one is, the beginning of a gap, definitely. And the two categories work also very differently here. Timer. Okay, if you recall in RDT 3.0, we need a timer in order to tell whether a packet is dropped or not. Yes, go back N and selective repeat, both of them implements timer. Okay, but in selective repeat, there's one timer for each packet that is still in flight, not yet acknowledged. Okay, so one timer, one packet. But for go back N, there's only one timer for the oldest unacked packet. So in one round, there'll be a lot of packets being sent, multiple packets being transmitted. Okay, there's going to be just one timer for the oldest unacked, meaning if you send one flight out, there's just going to be one timer for the first one in that flight. Okay, and if the first one is acknowledged, there'll be a timer for the second packet, that is now the new oldest packet that's not yet active. Okay, so one timer for a flight of packet in go back N. And the last difference is this. Okay. For selective repeat, when timer expires, the sender only retransmit the unacked packet. So whatever that timer says, if this is for sequence number 10, then it only retransmits packet 10. But in go back N, when the timer expires, it's going to retransmit from that oldest unacked packet. So all the unacked packets from the oldest one to the newest one. All right, so each timer is going to trigger retransmission of the rest of the flight of the packets.
All right, so that's the overview of the two protocols we'll be covering today. So let's go ahead and start with the first protocol, the go back N. The one that's treating a whole flight of packets as one, okay, a train. Okay, so you see that the timer is associated with the whole train. When the timer expires, the whole train gets retransmitted. Okay, so go back N is such a pipeline RDT. Now, the overview video that talks about go back N's mechanism is going to come in 3 parts. You want to pay attention to these 3 parts because quiz 21 is coming right after this, and quiz number 21 is also a fast solver gets bonus quiz. Okay, so let's start by introducing, in go back N there's this thing called the sender window, because now we send multiple packets. the sender needs to reserve certain memory space to hold these packets, right? Because these packets need to be held here until the receiver acknowledges that they are all received. Otherwise, you cannot remove the packet from the buffer because it might need to be retransmitted. Okay, so that window, the sender side buffer.
Now let's look closer into the first categories of the pipeline RDT to go back in. So this is just the sender side, and we'll come to the receiver side in a couple slides. And first thing first, the packet sequence number and go back in. If you recall in RDT 3.0, we only allow one data packet goes in out without being acknowledged, isn't it? And in that case, we just need one bit sequence number to tell the old packet and the new packets apart. But now go back and being a pipeline RDT, which we allow multiple packets being out in transit without being acknowledged. So your intuition should also tell you that, hey, you need a higher number of sequence numbers to tell all these in-flight packets apart. You are correct, and we now definitely need more, and k here is obviously larger than 1. Okay. Now, having k bits in the packet header, okay, as the sequence number field, then you see the sequence number can range from 0 all the way to 2 to the power of k subtracting 1. And next, in go back in, or generally the pipeline RDT, we do have this thing called the sending window. And the sending window is usually associated with the limit, okay, we call the n, or the sending window size. Okay, so n here is to limit the number of unact packets allowed. Right? And go back in, this is the number of consecutive unact packets allowed. It's also illustrated here. Okay. From the first packet in flight to the last packet in flight, the max range is n. Right? So at any given point in time, we allow only up to n packets being in transit, not yet acknowledged. And so you see here, this thing is also called the sending window, right? And n here is the sending window size. Now let's take a closer look at the plot over here. So each of these slim rectangles are packets. So the green packets are the very early packets that are already sent and already acknowledged. So this is in the middle of the sender transmission, as you see. Okay. And yellow packet, starting from here, the send base. So this is the first packet that is being sent out and not yet acknowledged. And there will be a number of these. So yellow ones are the packets already generated and sent, but not yet acknowledged. Okay. Now, depending on the application level source, the message could be large or small. Okay, so this is illustrating a case when the message is not that large, meaning you don't need to generate that many segments at the transport layer to cover the entire message. So potentially, within the limit n, we might have some sequence numbers that allow us to generate packets to send out, but we don't really need them. So the blue ones are usable, but not yet sent. Okay, so essentially, yellow plus the blue ones should be less than n. All right? Now, to indicate the beginning of the usable packet sequence number, we use yet another variable, the next seek number. Right? So send base, or sometimes I just call it the base, okay, is the base of the sending window. Next seek number is the next available sequence number that we can generate data packet within the window n. All right. And the last one, so these blank ones are simply outside of the window limit, so not usable, right?
Okay, so that explains the sender window. So there will be yellow packets and the blue packets. But sometimes there might not be any yellow packets at all, especially when the application layer is idling, not having any data to send. You can imagine the sender side here having a window of n, but all of them are blue because there's no data to be sent. Okay. Now, the second part of the overview, this window here may slide over as some of these yellow packets are acknowledged because they turn green, right? Then you need to move the base. Okay, sliding window.
And here, let's assume, okay, send base here finally receive an acknowledgement and it's acknowledged, so we turn this into green. What do we do here? Now this one is green, isn't it? So send base is only to indicate the first NACK packet, so we actually need to what? Change it to this packet sequence number. Right? As a result, we shift the window and it's beginning from here and include the next blank packet and turn it what? Blue. So the window is actually sliding over by one packet. Okay, so such a window is also called a sliding window mechanism. So when acknowledgement packet is received, you see these yellow packets turning green gradually, okay, and the window sizes is sliding over and then casting more blank packets into blue ones. All right. Just to make sure that it's clear, send base is the variable in go backend sender that always points to the base of the sending window, which means it's always the first yellow packet's sequence number. So the send base will only be changed when the first yellow packet is acknowledged and turned into green. So send base can no longer be pointing to a green packet, and as a result, it needs to be moved to the sequence number of the first yellow packet now. Right? And you see window then here is sliding over by 1. The next seq num is always pointing to the next sequence number in case we need to generate a new data packet. So in this scenario, it's pointing, of course, to the first blue packet that is useful and not yet sent. So because when we get a call from above and if we need to generate a data packet, then we'll turn this blue one into yellow. And the next seq num is going to be shifted over and reassigned to the first blue packet after sending. And we do not shift the window size at all because the send base is not changed and the n here is a constant. But be careful though. There'll be scenarios where, hey, all these blue ones are actually yellow, meaning, the sender does have large message to send and we are actually exhausting the entire window size to send the message already. In that case, the next seq num will be pointing here at a blank packet. Okay, that is the next available sequence number to generate a data packet. But it's not quite yet pointing at the blue one because, there's no blue packet at all. All right, so next seq num, to be very precise, it's just to point into the first sequence number in case we need to generate another data packet.
All right, so now you should have a good idea of the sender window. Now, the third video, briefer, only 2 minutes, just to repeat a little bit what we've talked about, the go backend's transmission mechanism.
The rest of the go backend you heard a little bit already about. The ACK, the sender received, is going to be a cumulative ACK. Okay? What it means is that in the sequence number of the cumulative ACK, it indicates all the data packets before this number n are acknowledged. Okay, so all packets before n, including n, are green. All right. Now, if the sender receives duplicate acknowledgements, so hey, ACK n has already been received, but the next moment, another ACK n is received. What does that say? If you recall earlier, that usually meant, packet n+1, there is a gap at the receiver. And receiver does not send acknowledgement up to sequence number n if there is actually any gap before it. Right? So receiving of a duplicate ACK at sender side indicates, whatever n is plus 1 is a packet that's missing. Timer. There is only one timer for an entire flight of an ACK packet. So it's a timer associated with the base, of the in-flight ACK packet train. Okay, so that is essentially this. The oldest in-flight ACK packet is always indicated by the send base. In a way, there's a timer associated with the send base, essentially. Whenever the send base is changed or whenever the send base is refreshed, we refresh the timer or restart the timer. If it's been unfortunate and we do have packet loss such that the timer needs to time out, then we retransmit the entire flight of packet starting from n all the way to the highest number that's not yet ACK. So that means starting from the send base all the way to the last of the yellow packet. So timeout indicates the entire flight of the yellow packets will be retransmitted.
All right, so that's go back and sender. Okay, the general mechanism. Now, let's go on to quiz 21. But before that, Justin was asking, is non-pipelined RDT equivalent to pipeline, pipeline system with n equal 1? You know what? It is. Yeah. So the non-pipelined RDT or stop and wait RDT is a case of the more general pipeline system when n equal 1. All right, so let's go on to quiz 21. Okay. Hey, this look familiar, right? So this is the center side window. So I'm asking you to tell me the values of these three variables. Okay, so currently the scenario says send base is 23. Next seek num is 33. And the first grade packet, first grade packet is 39. Okay, so Q1 asks, what would these three values change? Or what would these three variables value change if we send 2 more packets? Q2, independently, starting from send base being 23, next seek num being 33, and first grade being 39. What happens after we receive an ACK? Oh, in go back and ACK is what? Cumulative. Okay, what does that mean? Okay, if we receive an ACK for sequence number 31, okay, what would these three variables value being changed to? Similarly, okay, Q3. If we suddenly receive an ACK, that is sequence number 32, what would the center side window change? Meaning, what would these three values change? All right, let's go to the score. Channel WA, quiz 21. All right, guys, okay, fast solvers get bonus. All right, so how about 4 minutes? Okay, let's start counting time. But again, fast solver with the correct answers, please. Ooh, very fast. All right. Okay. Kevin? Guys, what do you think? Kevin's answer? You're right. Justin? Not bad at all. Not bad at all. I'll take your solution. As I actually meant that the three events are not really happening in sequencing time. Okay, that is why in Team 5 and in Team 2 solution, their next seq num for the Q2 and Q3 remain at 33. Okay, but I see that you understand. Okay, how the window slides over. Similarly for you, Sylvain, very good. So is Tao, and I think Tao is teammate. Okay, Jiabao is also correct. Very good. There you go. I think this one is less tricky than quiz 20. Okay. Yeah, sorry for giving you guys all these tricky questions this early in the morning. Okay. Yeah. So let's go on. Now with the exercise, you guys should have a better idea of go back in and how that window slides over. Let's now show the finite state machines. So the sender side of go back in, really complex. Okay, we'll take it slow. Okay, I'm gonna run the video in 3 parts as well. The first part is in fact to review RDT30. Okay. So you are recapped how RDT30 finite state machine sender is like. And then we go on and derive the sender of go back in. So this video, a review of RDT3.0, only 2 minutes.
Go back and sender's finite state machine. Before we start talking about this, let me review RDT3.0 sender's finite state machine. And here it is, the RDT3.0 sender. Okay, so we're starting here, okay, and there are 4 typical transitions, 1, 2, 3, and 4. So first is to get a call from above. We generate the packet starting from packet 0, send it out, and then start the timer. The other is getting a feedback from the receiver. If it's not corrupted, and it is indeed the ACK we're expecting, then that's a positive acknowledgement, so we stop timer and move on to send the next packet. Third is when it's a little bit unfortunate, the packet is not correct or not arriving at the receiver, timeout will be triggered. So we retransmit the packet and start the timer again. Last one is when you get the feedback, it's unfortunately corrupted, then we do nothing. So we kind of ignore these 2 conditions on purpose. The second condition is, yeah, we get an ACK all right, but this is what carrying 1, which indicates this is a negative acknowledgement. So in these 2 cases, instead of quickly retransmit, we just ignore. Right, so this is a quick refresh of RDT 3.0.
And now, sender of go back in.
In go back in sender finite state machine, we also have these 4 transitions. Getting a call from above, receiving feedback from the receiver, and it's not corrupted. Having the timeout event, as well as getting feedback from the receiver, but it's corrupted. Okay, very similar. And then we go through them one by one. Now let's start from the getting a call from above transition here. Comparing to RDT 3.0's getting call from above transition, this one is pretty long. Yeah. And it starts from a if-else condition check. And the condition is this guy here. If the next seq num is less than base plus n, so base plus n is what? The window range, isn't it? If the next seq num is within the range, that means, okay, we can now generate still some data packets. So, makes sense. We go ahead and create the packet using the data from the application layer, generate the checksum for the data, and then give it the sequence number. Okay. Here. We are now using an array of send packet here to store all the packets being generated. This is because go back n is a pipelined RDT, meaning there will be multiple packets in flight, so they'll be generated, being transmitted, but not yet acknowledged. So these send packet will need to be stored temporarily at the sender before they are acknowledged, because chances high that you need to retransmit it somewhere later. Okay, so we need an array instead of just one packet there to store the packets that are in flight. Next step, send the packet out. Oh, and then we need to start the timer, right? This is to handle the cases we could have packet losses. Just like in RDT 3.0, the difference to RDT 2. something is to have these timers. So we need to start timer, definitely. But in go back in, we have one timer for the entire flight of NAC packets. So we need to check, right? We cannot be starting a timer for every data sent. So here we're checking. If the packet we are now generating is indeed the base, the first yellow packet, because the timer in go back in is associated with the first yellow packet, so associated with the base. So only when the packet we are generating is the base, then start timer. Otherwise, don't. So this ensures that we have only one timer for one flight of NAC packets. And the last is straightforward, just increment the sequence number by 1. Right? So this is if the next seek num is within the window. Otherwise, refuse data. So this is telling the application layer process saying that, hey, I cannot be sending more data packets. So you hold on and you try calling the RDT send after some time. And the second one that we'll examine is this guy here. All right, so this is supposed to be the case where we receive acknowledgement, and it's a new one, therefore we could move on. All right, so let's take a closer look at how the move on is like in go back and sender. First of all, the checking condition. Get the feedback packet coming from the receiver from the lower layer. And if it's not corrupted, oh, good. So the feedback packet is not corrupted. So this must be one of those cumulative ACKs. So inside the ACK, there's going to be carrying a sequence number. So why don't we get that sequence number out? So get ACK num. Okay, so this is a new function call introduced into go back and's finite state machine. So that is just a bit abstract, but what it does is to get the sequence number in the cumulative ACK packet here. All right. And we simply change the base to that sequence number plus 1. All right. So this is the first packet that is unacked. Hey, makes sense, right? Receiver sends a cumulative ACK. So that ACK carries the sequence number n, which indicates all the sequence numbers before that, including n, are acknowledged. And the n plus 1 is the first in the gap in the receiver. The first one, that ACK cannot be acting. Okay, therefore, base is assigned to that value. Okay, makes sense. Oh, but we check. So just like in the generating data part, there are a lot more check. Being careful here. If the base is nulled, the next seek num. What does that mean? Base should be the first yellow, and next seek num should be the next data that is allowed to send. But next seek num cannot be a yellow packet, right? So if they are the same, that means there are no yellow packet at all in the window. Okay, which means all the packets that's not yet act at this point in time are already act. Okay, so stop timer because there's no pending packet waiting for acknowledgement. Otherwise, restart timer. So we receive a cumulative ACK. The base is reassigned such that it's pointing to the first yellow packet. Okay? And so we refresh the timer for the first yellow packet for the base. Okay? So restart timer. Right? So the only thing that's a bit odd is this. There's an if condition to check whether we should stop the timer because all standing packets are cleared. All yellow ones certainly turn green. Or we need to refresh because the base is either refreshed or changed to a new value. And therefore, we need to restart the timer for the refreshed first yellow packet.
All right, so those are two of the major transitions. There are two more. You see that there are two more arcs. So let's hold on to that last video and take a rest now. Okay, 10 minutes break. It's now 11:13. Let's resume at 11:23. Okay, break. right, so let's come back to the lecture. Yeah, there's one more video, but it's very short, still about the sender, because there are two more transitions we're yet to talk about. And kaze, the receiver, is coming up after this video.
And the third transition is straightforward. It's actually very similar to RDT 3.0's timeout event. Yeah, we restart the timer and retransmit the packets. In RDT 3.0 sender, we retransmit only one packet, but this time in go back in, we retransmit for the entire flight of packets starting from the base to the packet right before next seek none. And the fourth transition is this: when the sender received a feedback and it's a corrupted feedback, then we do nothing. So this is just like in RDT 3.0, when the sender receives a corrupted ACK or a duplicate ACK, which is a negative ACK, it does nothing. Okay. Now the difference here though is that it only handles the corrupted ACK case. What happened to the duplicate ACK? In go back and sender, yeah, it's actually handled here. When the sender receives an ACK, it's not corrupted. Whether it's a new ACK or a duplicate ACK, the actions are the same. If it's a new ACK, the base will shift to the right. But if it's a duplicate ACK, if it's a duplicate cumulative ACK, the base will remain the same. Right? Would this be a problem? Now, some of you might not be very comfortable with this, right? Because, hey, if the base remains the same, what do we do here? Yeah, we'll be definitely in this situation, right? Mm-hmm. Yeah, there's an unact packet somewhere and the base remains the same. Mm-hmm. We'll be restarting the timer, meaning the first time that base is receiving an ACK for all the packets before the base, the timer for that base has already been started. And now we're reassigning the base to the same value and restart the timer. That means we're extending the timer interval for that base. How do you like that? Think about it. And the last bit of the go back and sender, or shall I say the first bit of the go back and sender that we actually taught last, is the initialization of the sender. Okay, so the base, starting of the window, is initialized to sequence number 1. Next seek num is also initialized to sequence number 1. So this is unlike the RDT 3.0 sender receiver, always starting from packet sequence number 0. In go back and sender, textbook authors decide suddenly that they want to start from the sequence number 1.
Okay, good. So now finally, the receiver's finite state machine.
Now, the receiver finite state machine of go back in. It's actually quite simple. Let's just skip the initialization and focus on the two transitions possible. Among the two, this one is the more straightforward. We receive the data, get a call from below, and check the data, it's not corrupted, and check the sequence number of the data. Has seek num there is a function newly defined for go back in again. So what it does is simply checking the sequence number in the data and see if it matches the expected sequence number, which starts from sequence number 1. So if we receive packet 1 and it's expected, extract data out of packet 1, pass the data up to the application layer, generate ACK packet for packet sequence number 1, send the ACK out, increment the expected sequence number. Okay, so this is the simple case where everything works as expected. No error, no loss. And the second case is the default transition. What default meant is just all the other conditions that's not matching the previous transitions condition, which means the data can be corrupted or the data received not corrupted but not carrying the sequence number expected. So here, corrupted data or data packet that's not in the expected sequence number. Now this could be a duplicate data packet. This could also be a data packet carrying the future sequence number. So in either case, which means default is just to send the same packet again. That is the packet generated here, which is the ACK packet that is generated previously when data arriving correctly and in sequence. So in case of corrupted data, out of order data, we discard the data, no receiver buffering, So there's no extract of data, no passing of the data up to the application layer. And all we do is simply react, okay, to the data with the highest sequence number arriving correctly in order. So go back and receiver there. Works a bit odd, not that intuitive, but it's very simple. Okay. It always acknowledges to the data packet that is the highest in sequence number for all those who arrive correctly and in order. So all the receiver needs to track is the expected sequence number. And that's pretty much all. At the sender side, if a duplicate ACK is received, that is essentially saying either the data previously sent is corrupted or the data previously sent is lost.
All right, so that was the entire go back in. Before we go on with the example, there was a question from Kaze asking when the packet arrived out of order. Okay, a later packet arrived before the previous packet arrived. That is called packet arriving out of order. Now you heard from the receiver's finite state machine, we discard that packet even though it has arrived and it's correct. So you can imagine in go backend's receiver, we might be dropping some packets, especially the ones that's arriving out of order. Okay, and we send duplicate X to the sender to let sender know that there's a gap. Okay, so I was expecting this packet, but no, I get that packet plus one sequence number and so on and so forth. Okay, so we discard the packet and send back a duplicate acknowledgement indicating negative. A particular packet, that packet I'm expecting is not coming. Instead, some other packet arrived. Okay, good. Now let's exercise go back in with an example. The example is not that hard, but as you can see, go back in mechanism's complexity is higher. So this example, although simple, it's going to take longer time. So I'm breaking it into two parts. All right. So this is the first part, deriving through the example.
Next is to walk through an example of go back in, following the finite state machines. So then we go back and recap, go back and sender's finite state machine and the receiver finite state machine, just so that you can follow. And real quick, the sender side of go back in is this. If we get a call from above, we check real quick whether next sequence number is within the sending window, which is base plus n. If it is, okay, then we generate packet and send it out. And then check whether we should be starting a timer. And the condition to start the timer is if this next seq number is indeed, okay, the base, and then increment the sequence number. All right, so check whether the next seq number is within the sending window. If so, generate the packet, send it out. Check whether we should start the timer. So next seq number, whether it equals the base, and then increment the next sequence number. If we do not pass the condition where the next seq number is within the sending window, then ask the application layer process to wait. All right. Now, back to the example. Let's assume the window size is 4, okay, and the sender's application layer process is sending data all the time. So sender here gets call from above all the time. So let's see. In the first call from above, all right, the base and the next seq number are both initialized to 0. Okay. Now the first call from above is going to trigger, checking whether the next seq number is within the sending window. Sending window starting from base and window size 4. Next seq is initialized to 0. Is 0 less than 0 plus 4? Yes. So we generate the packet, send it out. And next to what? Check whether we need to start the timer. And the condition to start the timer is only when the next seq number equals the base. Next seq number is 0, base is 0. Cool. Okay. Packet 0 is indeed the first of the first flight. So start the timer here. All right. And next is just to increment the next seq number to what? 1. So next sequence number here at the beginning is 0. Now increment it to 1. So if we get a call from above again, next seq number, is it less than base, still 0, plus 4? Yes. So generate packet 1. 1 here is the next seq number, isn't it? Send it out. Check whether we should start the timer. Next seq num is 1. base is 0, not matching. So the second packet in flight does not start timer. All right, just increment the next seek num. So here, the third call from above will start from next seek num equal to base 0 and 4. Is 2 less than 0 plus 4? Yes. So we generate yet another packet. Next seek num equal to, send it out. Do we start a timer? Next seek num equal to base 0, therefore not matching, not starting timer. Increment the sequence number to 3. Right? Is 3 less than 0 plus 4? Yes. Generate packet 3, send it out, not start the timer because next seek number is 3 and base is still 0. Right? And we increment the sequence number to 4. And now we get the fifth call from above. And that call from above will check, is 4 less than base 0 plus 4? It's no longer less, right? So what do? We go to the refuse data part of the if condition. So yeah, the application layer process is asked to wait, and sender will pause sending for now. And these packets will go out to the internet and hopefully reaching the receiver, while there's a timer that's ticking and ticking, ticking, and that is associated with the base, the packet 0. All right. And here's to quickly review the receiver of go back in. If we get a call from below, the data is not corrupted and carrying the expected sequence number, simply extract data, pass to the application layer, generate the ACK, send the ACK, and increment the expected sequence number. And otherwise, just resend the ACK that has been generated previously. Now, the receiver. Okay, receiver here will be receiving packet 0. Yeah, it's not corrupted and it's expected, right? So expecting sequence number 0, receiving sequence number 0, therefore we send ACK, expected number 0. Next, yeah, we get a call again from below, packet 1, not corrupted, and it's in sequence, therefore we send ACK for the highest data number that has correctly arrived and arriving in order. So these are being sent back to the sender. But packet 2, oops, is lost somewhere on the internet. But packet 3 will arrive. It's not corrupted, but is it expected? We're actually expecting what? Sequence number 2. So we do not extract data. We actually trigger the default transition, if you recall, and just resend the ACK that is previously generated. So ACK 1 is being sent again. So right here. All right.
All right, so that's the first part. Okay, just to send a string of packet and receiver reacting to receiving a sequence of packets. So in this example, there's a gap in the middle. Now, let's continue with that example.
And now we come back to the sender side. Okay, we'll be receiving ACK 0 here. All right. So receiving ACK 0, it triggers sender finite state machines. Oh, the transition at the bottom, isn't it? Receiving a call from below. Yeah, receiving a feedback packet from below. What do we do there? Yeah, let's recall and go back. Yeah, so here, quickly recall. Okay, this transition, getting a packet from the lower layer and it's not corrupted, what do? Set the base to the sequence number in the ACK packet plus 1. And then we check whether we need to stop timer or refresh the timer. Now, only when the base and the next seek num are equal, then we stop timer, because the base here is empty, meaning no yellow packets at all, because next seek number is the first blue. So only when the base and the next seek number are the same. Otherwise, restart timer. Okay. Now we can come back here to examine. Yeah, what is the action the sender should be taking? Okay. First, receiving ACK 0. So that's triggering the transition at the bottom, a feedback coming from the lower layer, and it's not corrupted. So what we do is to extract the sequence number in the ACK, add it by 1, and that will be the new base. So base here is moved by 1 position. The next thing we do is to check whether the base equals the next seek num, right? If they are the same, that means we should stop the timer, because hey, all the data packets are already added. Right? But otherwise, then we restart the timer. So, hey, base is 1, next seek num was previously 4, isn't it? That's why we are waiting here. Okay, so, we cannot be stopping the timer. Instead, we should what? Restart the timer. So, this timer here, original ticking, will be canceled and we restart the timer here. And that timer is going to be associated with the new base, which is 1 over here. All right. And then, hey, sender is trying to send data. So quickly get a call from above. So we trigger the top transition. Right? So next seek num is 4. And 4, is it less than the base 1 plus the window size 4? So together 5. 4 less than 5. Cool. We can generate packet 4 and send it out. Is the sequence number base equaling the next seek num? No, so we do not start timer here. All right, so base is 1, so that means base, there's already a timer running. All right, next seek num, 4, not equaling 1, so not starting a timer here for generating packet 4. So timer is still associated with the base 1. All right, and then we increment the sequence number by 1, so 5 here. Similarly, receiving ep1, we set the base to 1 plus 1. So the base is now what? 2. Is the base identical with the next seek num, which is 5? No, therefore we do not stop timer, but instead we restart timer, so t removed there, and t is restarted with the new base, that is 2 over here. Okay, so t for 2. So this is t for 1, and this is t for 0. And at this point, one slot open up, getting call from above. Yeah, 5 is less than 2 plus 4, 6. Therefore, we generate packet 5 and send it out. And do we start the timer? No, right? And increment the sequence number to 6. And yeah, another ec1 is coming in. Okay, this is triggered by receiving packet 3 without packet 2. So ec1 comes in, triggering the bottom transition, not corrupted, set the base to 1 plus 1, 2. Well, that is the same. All right. Base and next seek number, still not matching, therefore we restart timer. Ooh, so hey, we actually killed the old timer for base 2. Now, restart timer for base 2. That means, wow, this base is actually, waiting a longer time to expire to retransmit. But it's okay. It will still work. Just wait a bit longer. Right. If we get a call from above now, all right, next seek is 6, and base is 2. 2 plus 4, also 6. 6 not greater than 6. Therefore, we again wait here. All right. So, yep, pretty much wait here. And so this timer for the base 2 is going to tick, 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 tick. All right. Let's assume packet 4 and 5 arrive at the receiver side, which generates re-ec of packet 1 because they are out of order. And let's just assume these 2 acts is just going to take a long time to come back before t for 2, the second time here, times out. Okay. What's going to happen here is that it's going to trigger the sender side, the timeout event. What do we do there? We restart timer and what? Retransmit the entire flight of packets starting from the base. So 2, 3, 4, 5 go out at once. All right. And good thing is that at the other end, the receiver here finally gets packet 2. Yeah, it's finally the expected sequence number, so it's going to call the transition on the right, extract data, pass it up, so deliver to the application layer, and therefore we generate ep2. And packet 3 arriving here, extract data, and then generate ec3, and so on and so forth.
All right, so let's go back in. You see that the example is actually very simple. We're sending a window of 4 sending packets with just 1 packet drop, and it takes 12 minutes to walk through the whole example. Okay, now let's move on to the second pipeline RDT. It's called the selective repeat. Okay, although it's discussed later, but in Polly's opinion, it's actually the one that's a little bit more straightforward because you have one timer for one packet. So you kind of treat each packet individually instead of grouping them into a team, into a train. Okay. I don't know if it's a good analogy. Okay. If you work as an individual for an assignment, it's simple in a way that you are the one, okay, that's handling it. You don't need to wait for others to complete other parts, okay, before you can move on. But on the other hand, then you will have to do everything. So working in a team, okay, can be a little bit troublesome, right? You might need to wait for others to complete one part in order for you to do the second part. Okay. But on the other hand, if the task is straightforward, having a team, okay, divides work, divides effort. So SR is the other kind. Individual, we treat each packet individually. Okay. First is the introduction video. So the first part, it will sound like Polly is repeating, introducing SR again. Okay. But in the second part, you will see Polly explaining the sender window size. Okay. In selective repeat, because it's a pipeline RDT, so we need a certain buffer space at the sender side. In selective repeat, we also need a buffer for the receiver side, because if a packet arrives out of order, it should be treated individually. We need a memory space there to hold these out of order packets before the gaps are filled. When the gaps are filled, then you finally get the packets in sequence. Then you can extract data and send it up to the application layer. Otherwise, the application layer might get out of order bytes. Okay, so the message you sent originally might arrive and reads really weird in the end. Okay, so in SR, a little bit trade-off you see is that at the receiver side, there's also a need of buffer space. So let's introduce selective repeat.
Selective repeat. This is the second big category of the pipeline RDT. So its design is pretty much the opposite of go back in. So in go back in, you have cumulative ACK. So the sequence number in the ACK there is to indicate all the packets before this particular numbers are received correctly. But in selective repeat, the acknowledgements are individual. So one acknowledgement packet per data packet. The sequence number in the acknowledgement is only to acknowledge one data packet. In go back in, we have one timer for an entire flight of packets. When that timer times out, we retransmit the whole flight of packets. In selective repeat, the opposite. We have one timer per data packet. When that timer times out, we retransmit just that data packet. All right, so receiver will acknowledge each correctly received data packet individually. Sender will only retransmit a packet when the timer for that packet expires. Very straightforward. The slight tricky part of the selective repeat is at the receiver. Okay, we now have to buffer packets arriving out of order. And the reason for this is very straightforward, very simple. If we send packet 1, 2, 3, and 1 arrived at the receiver, 2 get lost, 3 arrived at the receiver. You cannot be just extracting the data bits out of packet 1, pass it out to the upper layer, and not passing the bits of packet 2, and immediately pass the data bits in packet 3, and then later pass the data bits in packet 2, because that way you get bit sequences that is out of order in the application layer. And our definition of RDT is that all the bits arrive reliably and in order. So receiver here in selective repeat, the implementation gets complicated. You need memory space to store temporarily the packets arriving out of order. You wait until all the gaps are filled, and then you pass all the data bits up to the application layer in sequence. The only thing that remains the same is there is still this sending window, which is limited by n, from the base to base plus n. Now, be a bit careful in selective repeat though. What we are limiting there is the sequence number of the unact packet. So what is the maximum sequence number there can be unact. As opposed to in go back n, we say n being the number of unact packets. Right? The reason that I'm saying you need to be careful is because of this. From the base to n plus base. Yeah, there are yellow packets, all right, and after the yellow packets, the blue packets. In go back n, they're just gonna be yellow and blue. So the number of yellow packets maximum will be n. In selective repeat, because we have individual acts, so some of the yellow packets can be green, like this. All right. So even though they're turned green, but that doesn't mean that they will include these four, okay, into the window, like this. Okay, no. So what we're restricting is the maximum sequence number that can be an act, not the maximum number of packets can be an act. Okay, just to make sure that's clear. And the receiver of selective repeat is, as we talked about, more complicated. It also maintains a certain data structure, tracking the status of these packets. So we also have a window size here at the receiver. The base is now called the receive base. So receive base is always pointing at the first packet expected but not yet received. And there could be a number of these pink packets around. So these are the packets arriving okay, but out of order because there's a gap before it. So those are the out of order buffered packets. The blue ones are reasonable, okay, packets that are expected next. Okay. The black ones are just not possible. So if we receive packets after receive base plus n, we'll be just treating these as maybe hackers injected packets, spoofed packets, things like that.
All right, so you see the receiver side also has a window. Okay, and then there are some gray packets, meaning gaps, and some pink packets. Packets arrive out of order but intact. Okay, so they are kept. Okay, until the gray packets arrive and turn pink. Then we have a whole flight of packet we can pass up to the application layer. Okay. Now, next video. So that was general mechanism. What about the finite state machine of selective repeat? You know what? We'll talk about it now. But unlike previously, we use circles to represent state and arcs to represent transitions. We're going to show the finite state in a pseudocode fashion, like a switch condition in C programming.
And now the selective repeats finite state machines. This is the sender side of the machine, and this is the receiver side of the machine. And you might be going, wait, they don't look like FSM at all, right? Because previously we have like states, right? And the number of transitions like these. Yeah, what I'm doing here is to do textual representation. So what I'm saying is essentially, yeah, there are still 3 transitions. So first transition is triggered by this event, the data from above. Okay. Second, the timeout event. Third, triggered by receiving an acknowledgement packet within a particular range. Yeah. So later on, you will see what's nice about writing the finite state machine this way, because it looks almost like a pseudocode, isn't it? Right? So the sender side is looking like a switch procedure, where when there's the data from above event switching in, then we do this. When there's the ACK packet being received switching in, then we do that. So now let's go over the finite state machines of the senders and receivers. Sender side, when there's a call from above, okay, if the next available sequence number is within the window, yeah, send packet. And you know how to do the next available sequence number, whether it's in window check, right? So the next seq num should be less than base plus n. Second is the timeout event. If our timer times out, and that is for packet sequence number n, we retransmit packet n and restart timer. Straightforward. If we receive an acknowledgement packet, we extract the sequence number and check if it's within the send base and send base plus n subtracting 1. So that is saying, hey, whether the ACK is within the reasonable range, right? Because the send window is only this big. If we receive ACK before that or after that, that's just weird. Okay, let's just ignore those. So we'll only be handling ACKs that's within the send window. Now, once that's the case, we mark packet n being received, so turn it to green. If n smallest unACK packet. So if N here is also the smallest unACK packet, so we turn that into green. There could be a number of other greens following that. Then we could what? Advance the same base all the way to the next yellow packet. Okay, so advance the window base to the next yellow packet, which is the next unACK packet. All right. So this is sender's actions, depending on what's triggering the sender's finite machine to take transitions. Similarly here at the receiver end, there are 1, 2, 3 transitions. First transition is if we receive a data packet that's within this range, the receive base and receive base plus n minus 1, so that is reasonable, okay, as expected. Then we send individual acknowledgement. So if it's packet n, then ACK n. If this packet is not expected, so meaning it's out of order, then we will buffer them. So these will be the pink packet, all right? Now, if this packet is actually coming in and filling one of the gray packets, so unreceived previously, but expected, then we can pass all the packets suddenly in sequence, all in pink, up to the application layer. So that's deliver those, okay, in ordered, and advance the window to the next, not yet received, but expected packet. So to the next gray packet. All right, so this is when we receive a data packet that is within the receiving window. If we get a packet, okay, that comes in, but it's actually in this range, receive base minus n to receive base minus 1. What is this? Okay. We are actually sending an ACK for that packet back. If you recall, it could happen, right? The ACK packet going back to the data center, if that packet is corrupted, the sender there is going to wait until the timer for that packet times out, then retransmit the data again. But that data has already been arrived at the receiver previously. And that's why the receiver sends an ACK back to the data at the first place. And that's before the data is found corrupted at the sender as well. Right? So in that case, we still need to send the ACK for that packet. Okay, do not ignore this. Otherwise, that timer is going to fire it again and again and again, and the sender there is going to retransmit the same packet again and again and again. Right? Third transition, otherwise, or the default, I'll just ignore. Okay, so receiver pretty much do nothing in case it's packet not within the receiving window or not one receiving window before. All right. So those that are outside, just ignore it because chances high that they're coming from hackers or previous connections, and the data somehow, the packet somehow gets stuck in the network for too long, and it's gonna be useless anyway.
All right, so that's finite state machine in pseudocode. Now you can probably imagine writing go backends finite state machine in such a pseudocode fashion. And guys, provided the pseudocode, we can give it out to the programmers and they'll be able to implement go backend or selective repeat sender or receiver. Okay, so the finite state machine there are to represent a computation process. Okay, it works just like the pseudocodes. Now let's exercise selective repeat with a few examples.
And let's also walk through an example of selective repeat, just like we did one for go backend. So that example in go backend is actually harder to analyze. This one, on the other hand, relatively easy. Now it looks very much like the example in go backend. So window size 4, and we start from base 0 and the next seek number 0. Getting a call from above? Yeah, because the next seek is less than base plus 4. Therefore, we generate packet 0 and send it out. And we go on until we hit next C equals 4. And that is not smaller than 0 plus 4 anymore, so we wait. All right. Now, over at the receiver side, scenario similar, receiving packet 0, but the receiver's action different. Okay, for packet 0, we send individual ACK 0. Receiving packet 1, we send individual ACK 1. Well, not getting packet 2, but we'll be getting packet 3. And out of order, so we buffer and send individual packet, individual ACK packet, ACK 3. So ACK 1, ACK 0, ACK 1, and ACK 3 will go back to the sender. Now, Sender, upon generating packet 0, packet 1, packet 2, and packet 3 will all start the timer individually. So T0, T1, T2, and T3 will all be ticking, no worries. Okay. Now, X0 now comes back to the sender. Sender receiving X0 will do what? Clear packet 0. So that packet will turn green. All right. Is it in sequence? Yes. So we advance window. Advance window by 1 to the next unact packet. Upon receiving packet 1, also, advance sequence by 1 because it's in sequence. And hey, so base is changed to 1 and then to 2. So that allows us to send packets more, right? So 4 is generated, 5 is generated, and they're being sent out. Well, packet 2 did not get acknowledgement, but we get what? ep14. All right. So what do we do there? Yes, we actually release packet 3. So we turn that into green. But hey, packet 2 there is still yellow. All right, so this green packet, packet 3, is not the smallest unact packet. So we cannot advance the window size further. We cannot advance the send window further or the base further. All right, so cannot be sending more, so still wait here. Okay, so this part of go back and selective repeat similar, right? But now, look, packet 4 and 5 will go to the receiver. Receiver here receiving 4, out of order again, buffer, send ep4. Packet 5, buffer again, send ep5, and those will go back. Here, timer for 4, timer for 5 will be fired because there's one timer for individual packets. Okay. So finally at this time point, timer for 2 finally expires and therefore we resend packet 2. Packet 2 goes out, received. Finally, this is the smallest unact packet and all the packets subsequenting packet 2, 3, 4, 5 can be passed up, okay, in sequence to the application layer. And we send back ep for 2. All right. So, simpler.
Okay, so you see that the same example for go back in, it takes 12 minutes to talk about. But the same scenario for selective repeat, a lot simpler, 4 minutes. Now, we are not quite yet done. Okay, so there are a couple more examples coming. And with these 2 examples, you might see that with selective repeat, we want to make sure that the window size and the sequence number there maintains a certain relationship. Otherwise, we might mistaken some earlier packets as a later packet or vice versa. Okay, so this one a little long, 6.5 minutes, but these 2 examples are very important.
The last bit of selective repeat is this. Let me show you this case. There are 2 scenarios, okay, but from the reviewer's point of view, they will actually look the same, right? And this is due to the fact that the sequence number here, the sequence number space, and the window size there is not set in a way that we could tell individual packets apart. Those who are sent earlier versus those who are sent recently. Okay, so the example goes, sequence number, only 2 bits, so there are only 4 different numbers. Window size, 3. Right. So the selective repeat sender side will look like this. Well, the window size is 3, so we can only send 3 packets back to back of each other. So packet 0, packet 1, packet 2 goes out. Receiver here receiving 0, 1, and 2. They will then send back ep0, ep1, and ep2. So ep0 here arrives back at the sender first. And this is in sequence, so we advance the send base. And we generate yet another packet to go. All right. And the next ep, that's going to advance the send base further to 2. Right? And we generate yet another packet to send. And the next one will be what? Carrying sequence number 0. Now, if packet number 3 did not arrive at the receiver, all right, Receiver here will see, all right, I got the packet 0. And you know what? Within my window, I am indeed expecting someone carrying sequence number 0. So this one will be what? Buffered. And an ACK of 0 being sent back to the sender, isn't it? Right. So that seems to be fine. Yeah, this is the no problem case. Wait until you see the next one. Here's the next one. Same scenario, window size only 3, and we have sequence numbers. There are only 4 of them. So we send packet 0, 1, and 2 out. Receiver here generates ACK0, ACK1, and ACK2 back. But unfortunately, all of them are lost. So timeout is going to happen and retransmit packet 0. This packet 0 will go, and receiver here will say, hey, you know what? I'm expecting packet 0. It's within the receive window. So buffer and send back ACK for 0. Sounds familiar, isn't it? Because that's exactly what's being done here in the first scenario. So from the receiver's point of view, identical. Also, buffer the packet and send back ACK0. But the thing is this, at the sender side, you see, this packet 0 is a retransmission of the first packet 0. But this packet 0 here is actually the second packet 0, no longer the original, the first packet 0. All right? So if packet 3 here arrived at the sender, the sender is going to what? Clear that gap and pass 0 up to the application layer. Before that, pass, of course, packet 3's bits into the application layer. So 3 and 0's data bits will go to the application layer. But look here. Now, this is packet 0. When packet 3 finally comes here, it's going to clear and send packet 3's bits as well as this retransmission 0's bits up to the what? The application layer. So you get unwanted duplicates. So you do have a situation here. From a receiver's point of view, it actually sees no differences in the two scenarios. You get duplicate data in the end in case B. So we need to be careful here to prevent packet 0 here and packet 0 here obviously are two different packets, but being confused as the same packet. Okay, so according to case A, we'll actually pass packet 0, these bits again to the application layer. Not good. Right? So in order to tell this packet 0 and this packet 0 apart, we have to think, what is the worst case? Okay, can we use a sequence number such that we will not be confusing this packet from this packet? Okay, so a new packet should be farther away, should be carrying a sequence number that's farther away from an earlier packet. And no worries, if you look at this, case number 2, case B here, is already the worst case that I'm illustrating. So in this case, we're seeing that the receiver is advancing the receiving window one after another. So the receiver is saying, hey, everything is okay, let's move on. But sending side here, not getting any ACKs back, hesitates and waits and waits and waits and not moving. So you have one end moving really fast and the other end staying. Okay? So you see in the end, the worst case is what? The sending window never really moved, but the receiving window moved the entire end. Right? So they're actually end apart. If you want to make sure that none of the packets still in the sending window will be confused with the packets in the receiving window, what do you need to do? Isn't it obvious? The sequence number, make sure that the space is larger than 2 window sides, right? Then, hey, packet sequence 1 will never appear again in the next window, in the receiver's window, right? So you will never have the trouble of confusing an old packet from a new packet. And that is why the sequence number space here needs to be larger or equal to 2 times the window size.
Okay, there you go. The sequence number needs to be 2 times larger than the window size. And you know what? It's time for quiz 22, but we don't have time to work on it in the lecture. Okay, so quiz 22 is going to be a take-home quiz. Okay, so what you're asked to do is very straightforward. You're asked to compare, go back in and selective repeat. Okay, so Q1 asks, which one is more bandwidth consuming? Go back in and selective repeat. And Q2 asks, which method tends to require more memory space at the receiver end? Okay. And which one requires more timers at the sender end? Both go back in and selective repeat need to maintain timers. Which one maintain more timers? By the way, timers are always at the sender end. And Q4, and this one might be a little bit tricky. If you are to program a pipeline RDT, okay, and the goal is so that you do it with minimum effort, which method would you choose to implement? And why? Why that particular mechanism would be minimum effort? Okay, good. With that said, guys, that's all the time we have, and I see you next week. Okay, goodbye. And next week we'll start by talking about the RDTs really implemented in TCP. Okay, the transport layer service that does provide reliable transfer. Okay, good. Bye. See you next week.